And Mathilde is a research scientist at Google AI. Her primary research interest is on large-scale self-supervised representation learning for vision. She did her PhD at the INRIA Grenoble and Facebook AI Research, where she published a number of very high-impact papers on self-supervised learning, including Deep Cluster, SWAB, and most recently Dino, which was a very successful transformer-based self-supervised learning framework. And so today she will talk about her latest efforts in this area. So please, everybody, welcome Mathilde.
Hi, everyone. So it's really my pleasure to be here to talk about self-supervised vision transformer. Do you hear me fine, or should I? Okay, I'm a bit small. Okay. So let's get started. So yeah, I'm right now at Google, but the work that I'm going to present today, it's work that I've done during my PhD, where I was at Facebook AI Research and at INRIA. So the current AI system, the current state-of-the-art system, they are trained on mostly on supervised datasets. And by that, I mean that each image in the dataset needs to come with either an annotation, so labeled by humans, or a caption, or some kind of external information in order to be leveraged by the model. So in self-supervised learning, what we aim to do is to learn from the images alone. And intuitively, we see that as humans, we are really able to capture some signals in these images, for example, to find common patterns like the mountain goats here, without having any external supervision. And so we want our AI agents to be able to do the same and to learn from just by observing the images alone. Moreover, annotating datasets can be cumbersome and expensive. It's an ambiguous process. There are many forms of valid annotations, and it's not clear what we should annotate. And therefore, it's a biased process and biased towards the decisions that the annotators take during this process. So it's possibly unreliable and noisy. And sometimes it's actually not even possible to annotate the data for privacy reasons, for example. So in self-supervised learning, we ask ourselves, can we train AI systems without any annotations? And more specifically, what we're trying to do is to learn representations from unlabeled data. And then these representations should be useful to solve downstream tasks. So here we really have to think about it as a two-stage pipeline, where first of all, we do the self-supervised training on images only without annotations. And then the second stage is to use those representations to actually solve supervised downstream tasks. And so examples of such downstream tasks can be object detection, semantic segmentation, copy detection, or image classification, for example. And so in self-supervised learning, what we do is that we design a learning task or a pretext task that does not rely on annotations. And the hope is that if the network is good at solving these tasks, then it would have acquired a good understanding of the scene and of the objects present in the images. And I think a good example of it is colorization, which was proposed in 2016, where they trained the network to colorize images given grayscale input. And you see that to train the network on this task, you don't need any annotations because the RGB information is already present in the dataset. And you hope that if the network can solve colorization, then it has acquired an understanding of kind of segmentation in the image to know which part should be colorized in which color. So recently, maybe the most successful self-supervised learning approaches have kind of converged towards a direction that we can call joint embedding architectures. And so here the motivation is that, the idea is that we apply different data transformation to an original image of the dataset, and then we train a deep network to use features that are invariant to these transformations. And so I think the original work for this was in 2014, where, and so a motivation for this is that most of the time, the way we see a scene does not really impact the semantic of that scene. So the way we the angle of the camera or the lighting condition for this image of a deer does not really impact the semantic of the concept of a deer. And so luckily for us, we can simulate many of these variation in the images with data augmentation, data transformations. And so there have been several successful implementations of this paradigm in the past years. And the original implementation was kind of parametric in the sense that the authors of exemplar CNN would train a huge classifier of the size of the data set to classify each image into its own class, and the class was formed by this image and all the transformation of that image. And so this obviously does not scale to data sets which have millions of images. And so contrastive approaches appear to circumvent this issue. And so in contrastive learning, what you do is that you form a positive pair. So usually by applying different transformation to one image. And then this positive pair has to be distinguished from a bunch of negative pairs, which are formed by different images of the dataset. And so here, to perform well, these contrastive approaches usually require a large number of negative pairs. And to have this large number of negative pairs, usually you train with a large batch or with a memory bank, and sometimes it's not very convenient. And so some non-contrastive approaches, so non-contrastive implementation of this paradigm have been proposed recently, where they show that you can train a model without the need for these negative pairs. And there have been also other approaches, other variants with clustering on nearest neighbors. And so here the motivation is to say that in a data set, there are some images that are close semantically. And so you don't want to push away images which might have a similar semantic. But talking about these different approaches is not really the focus of this presentation. So we'll leave it here. And so now I'm going to present DINO, which is a work that we published last year on emerging properties in self-supervised vision transformers with my former colleagues at MathildeCaron. And so in this work, we applied the most successful self-supervised approaches to vision transformers, and we observed a couple of interesting results, and which I'm going to present now. And so first, in the DINO approach, we actually use a particular training that we call multi-crop, and that we actually introduced 1 year before in our SWAV paper, and which was inspired by other related works. And so in multi-crop, what we're going to do is that from an image, we're going to take different views or different crops of that image. And the first set of crop that we use are what we call the global crop, and they will cover a large area of the image. So for example, more than 50% of the total image area. And the motivation here is that you hope that the main gist of the image will be contained in that crop. And so one of these global crop is going to be the target view, and it means that we will take other crops, and their task will be to predict the feature representation of that global target view. So we take another global view, and then importantly, we take a set of local views. And so this consists in zooms in the image, and they will cover only a small part of the original image. So for example, less than 50%. And so now we have a set of global and local views, and each of these views has to predict the feature representation of the global target view. And so here, I mean, intuitively, we think it's a good idea to predict crop from crop, and that it leads to global representation. Because here, if you think about it, what we do is that from one crop of the image, you need to predict another crop, the feature representation of another crop. And so the only way, I mean, there are two ways the network can do that. Either it's by outputting something constant for all images, then it's trivial to predict one from the other because they are all the same. But in these different models, there are different design choices or constraints to prevent the situation from happening. Or the other way is to actually output something about that image. And importantly, this something cannot be about the particular crop that is considered, because then it will have to be predicted from another crop of the image, which can be at another location. So that encourages the representation to be about something at the global level and at the global semantic level of the image. And then for the local views, we try to enhance that. And here, the local views, they will mostly contain parts of the objects. And so this way, from a part of the object, we want to predict most likely the object in entirety. And so this encourages object parts to object representation, so holistic representation. And we find in practice that this leads to good representations. So now let's look at some of the results that we have with self-supervised dyno training when we train with convolutional neural network or with vision transformer. And here we will consider two prominent benchmarks in self-supervised learning, which is linear and nearest neighbor classification on ImageNet 1K. And so here we pre-train the model with the self-supervised loss on ImageNet 1K with the labels for sure. Then we freeze the weights and we only either train a linear classifier with the labels, or in the case of nearest neighbor, we don't train any weights. We simply extract the features for our downstream data set with our pre-trained network. And then we perform classification based on nearest neighbors. And so this is the performance when we train the self-supervised model with a ResNet 50, so a ConvNet. And then we will apply the same self-supervised model with a vision transformer. So we take a bit small, which has the same roughly the same number of parameters and the same throughput as ResNet 50. And we see that on both benchmarks, we have an interesting boost of performance. And here, the interesting thing is that the boost seems to be even more important for the nearest neighbor evaluation, where we don't learn any weights. So there is no adaptation to this classification task at all. And so we evaluated this good KNN property on different variants of the vision transformer. And across the board, we outperformed the previous works that train self-supervised works that train either on ConvNet or on vision transformer for this benchmark. So this shows that there is a good synergy between our self-supervised dyno training and the vision transformer. And actually having a feature space which is good for similarity search, or where you can directly compute in this feature space the similarity between two images, has many applications. And one of them can be to copy detection, where you have a query and you want to find in the database the images which are duplicates or near duplicates of that image. And it actually turns out that dyno is very good at this task, even though it was not trained for it. And it's actually better than the same network trained with supervision, or the multi-grain architecture, which was trained especially for this task. Then another interesting thing that we can do with self-supervised vision transformer is that we can visualize the attention map that we obtain. And so here what we do is that we look at the attention of at the last block of the vision transformer of the class token, which is looking at all the patches, all the patch tokens. And when we look at this attention map, we see that it's naturally well segmented. There is a kind of a foreground background segmentation that emerges, and we can apply a threshold on that attention map, which gives a segmentation mask for free. And so here I say for free because the network has not been trained with supervision, nor has it seen any labels during its training. And so we can apply this to different images. We have some quantitative measure to evaluate those masks. And we can also compare to the same network trained with image classification, so with supervision, or with other self-supervised approaches. And what we see is that this property seems to be common to the different joint embedding self-supervised learning approaches and does not really emerge with the supervised vision transformer. So we can apply this, we can look at the attention map for different frames of the video. So here there is no temporal understanding at all. We are applying this frame to frame. And so there have been some follow-ups that show how the segmentation seems to emerge from this self-supervised vision transformer. And some of these follow-ups are actually going to be presented here at CVPR. So I think I encourage you to check this paper out. So now for the second part of this talk, I'm going to talk about MSN, so Masked Siamese Networks for Label Efficient Learning, which is a work that which is currently under review and that I've been working on with my former colleagues at Meta.ai. And so now let's go back a bit to the motivation of this talk and of self-supervised learning, where we want to learn representations which are useful for downstream tasks. And so something that we would like to have is that the adaptation to this downstream task can be done with only a few labels. And so maybe a motivation of why we want that is that as humans, we can efficiently learn to recognize objects from only a few examples. And here I put a screenshot of one of the slides from Nando de Freitas at his introduction of machine learning course at Oxford. And I remember this slide very vividly. And so here he showed that as humans, even, in this database, we only see 3 examples of a tufa, but oh yeah, you see my pointer. And so actually, as human, only by seeing these 3 examples, we will most likely be able to say that this is, we think, not a tufa, but this is likely to be a tufa. And so we would like our artificial AI and our AI engines to be able to do the same. So now we seek to, we were wondering what is actually missing to Dino to have, to enhance this few-shot property. And here what we did is, so the path from Dino to MSN is actually to add masking. And so we got inspired for this by recent work in Vision Transformer, where they apply masking, they use masking as a pretext task. And so here, if you remember, that's what we were doing with the Dino training. We had a target view, a global target view, and then a set of global and local views that needed to predict the feature representation of the global target view. And so now we will replace this global view by actually random masking of an image, which is kind of we can see it as a more aggressive data augmentation, where we don't just take a crop in the image, we actually discard more information of the image with this. And then the local views, actually we can reinterpret this as a form of masking, which we call the focal masking, but in practice it's exactly the same. And so with Masked Siamese Network, it's an implementation again of this joint embedding architecture in self-supervised learning. And here what we do is that we have this target view and we want to predict its feature representation from a masked version of the image. So either with random masking and with focal masking. And so doing masking has 2 main advantages in our implementation. The first one is that it reduces the device memory utilization and speeds up the training because you no longer need to compute the full sequence of patches. You can actually compute only, you compute only the output for the non-masked images. And so if you keep only 30% of the patches, so the masking ratio is 0.7, then the throughput increases a lot and we use less memory. So it allows to scale to bigger models and also to larger resolution. And also we find in practice that robustness to masking makes the features more discriminating, and we found that this is good for low-shot classification. So let's look at the results that we have. And so here we perform low-shot learning on ImageNet 1K. So we evaluate different self-supervised models, and what we do is that the network is pre-trained with the self-supervised loss. so with MSN without any labels, and then we train only a logistic regression with 1% of the labels from ImageNet, which corresponds in practice 13 images per class. And we see that we have a good performance on the benchmark, so we've reached the state of the art by using a quite small model, actually. And also, interestingly, here we use frozen features. So as I said, we only train a logistic regression on top of our features. So the adaptation is actually very quick and easy to do, and you don't need to fine-tune the whole network and find the different hyperparameters to do this adaptation. So that's more or less the same set of results here. So, but instead of using 13 examples per class, we use only 5. So you see my pointer, only 5, 2, or even only 1. So here, for 1, you need to think that it's as if we were shown only one example of what a tufa is. And we see that, for example, with only 5 images per class, when we reach up to 72% of accuracy imagination set, quite good actually. So present some quick ablations to the representation that have been learned with MSN, and we will show an addition to robustness to missing patches. And so here we show networks which have been pre-trained either with Dino or with MSN. And we compare different during evaluation, and means that during evaluation, none of patches will be masked. And here 0.7 means that during evaluation, we mask 70% of the patches. And we see that the Dino backbone, when we perform this evaluation, drops the performance by 4 points, 4% of one accuracy here on low shot evaluation. But the MSN network, actually has a drop of 0.2% top one in these benchmarks. And so to show this invariance to masking that we learned, here we show the cosine similarity between masked and unmasked representations of the same image. Also for the same, with the same network, either pre-trained with Dino or with MSN. And we see that when the evaluation masking ratio is up to 0.9, so we mask 90% of the patches, then the representation of only this 10% remaining patches for the same image is like 0.97 close to the representation of the unmasked image. So cosine remains high, and so it kind of shows the has learned to perform. And finally, if we have some time, we can show some qualitative analysis. And so here, actually, when you have a generative approach like MAE, you have actually have the model, but our discriminative, so it's not that obvious how to look at our features. And here, what we do is that we use the framework of RC which was proposed by Bord et al. And here what we do is that we train a generative model conditioned on our representation, and then we sample images from that generative model. And so let's take an example here where we have this image of a kangaroo. We take the feature representation given by MSN of this image, and then we sample from our generative model conditioned on that feature representation. And so how to interpret these samples? Well, what is common between this sample is actually what is encoded in the features, and what varies between the different samples is what has been discarded by the feature representation. And so here we see that what is in common between the samples is like the texture of the fur, texture of the kangaroo, kind of the shape, for example, with the ears, And interestingly, we also see that the model has learned to be invariant to the number of instances, because in the first sample, we actually have a generation with 2 or Siamese kangaroo. And what's the feature representation is invariant to is the background or the scale. Here we see the small or bigger kangaroo in this. And so here we do the same visualization, and on the first column you see the original image, and then we apply a mask. So we mask 80% of the patches, so only 20% of the patches remain. That's what we see on the second column. And then we sample from the generative model, which have been conditioned on the feature representation of the mask of the masked image. And that's what we get here in the last columns. And we see that, for example, with only 20% of the images remaining, the network has still retained a lot of semantic information. So, for example, can show the concept of a rooster or of a bird, a parrot in the middle. And we can also look at the image of the, and we see that in appear that actually makes sense, because if you look at the patches that remain, still the network has retained the information of the tree structure. And by contrast, when we apply the same visualization to Dino, which has not been trained to have this invariance, then the samples that we get have artifacts. So let's do a quick recap on what we've seen with this MSN. So we have shown that they produce representation that excel at low shot classification. We have set a new state of the art for low shot ImageNet 1K. And we have not talked about this, but it's a bit slow. But actually, we have good, especially good performance when we evaluate with few labels. But when we train when we transfer the network with many labels, then the comparison with other previous, with other self-supervised approaches is, we are performing on par, but not really better. And finally, we've shown that masking significantly reduces the training time and the memory consumption, which allows to scale quite easily the model to models with more parameters and images with a higher resolution. So that's it for me. Thanks a lot for your attention, and I'm happy to take any question if we have time, or to chat during the conference offline. Thank you.
So again, if there are any questions, please step up to the mic. Mathilde. Oh, right there. Go ahead.
Thanks a lot. Very nice work, very strong work, particularly the Dino work which you presented. There is a generic thing which contrastive learning approaches, and I would like your point of view on that. When we take these approaches and start to apply it on richer data set like VL genome with a lot of concept, then they don't perform really well. We notice that other approaches which are coming through, like autoencoder based approaches, they are slightly better. So do you think the local crop strategy which you are using in Dino can cater for that and can compensate for that, and that's the main reason of improvement in the contrastive approach you are using?
So thanks for your question.
Yeah, sorry, can you quickly you weren't.
Okay, so the contrastive approaches, when we used it on richer data set like VL genome, we noticed that they were struggling for the downstream task on multi-label data set with richer information. So the question is that Dino is a very strong approach, how that would put in context to that, and more importantly, the local crop which Dino is using, is it compensating for that, and is it the main reason for the better performance? And and better visualizations which we are seeing and experiencing in Dino. Thanks.
So thanks for your question. So I think, yeah, we train Dino on ImageNet, and usually in ImageNet you have one concept per image. And so when you take this global crop, you're most likely to have this main concept contained in the image, but then in the local crop, they will be kind of related to that concept. But then it's true that if you have an image with many things going on, but maybe the local crop that you will get will be about something which has nothing to do with your global representation, and then you might need to rethink about the modeling. But that being said, so when I was at Facebook, we trained this kind of approaches. So we actually trained Suave, our previous model, on images from Instagram, and so actually, so we were having this reasoning that maybe a lot of more are happening in the images, and we have this long tail distribution. So maybe we will need to rethink this multi-crop modeling. And so we tried different variants. And actually, the one that we found on ImageNet was the one which was working the best in our scenario. But I mean, I've never experimented with visual genomes, so I don't really have insights to give here. But yeah, I can imagine that you might need to rethink the model. Yeah.
Thanks a lot.
Yeah, and let's also do one quick question from the virtual audience. So I guess like the question is, do you think your method would also perform as well on uncurated data? So right now you're doing things on ImageNet, which contains some labeling bias. So have you tried it on uncurated data?
Yeah, so it's actually related to my reply to the previous question, where we actually train this self-supervised models on images from Instagram. And so when we apply on this dataset, we don't perform any curation or any filtering of the data. We just take random images from on Instagram, and you see that intuitively it has a very different distribution compared to ImageNet. And so if you take 1 million of images from Instagram, it's not going to look like ImageNet at all. And yeah, and I mean, we saw that, of course, we had a hit of performance compared to training from the very clean data from ImageNet, but we still are able to learn useful features. And also, maybe you can compensate the lack of data curation by the fact that you can actually train on much more data. And so we found that when we so we actually have a paper on this, but when we train this very large model, a self-supervised model on Instagram, and that we scale both the model and the dataset, we actually make up for the lack of curation, which was in ImageNet.
Okay. Yeah. Unfortunately, we're running out of time, so let's thank the speaker again for an excellent talk.